Button to start. There we go. Ready to go? Good evening, everyone. How exciting it is to be here in the classroom of the future. We're not in a physical classroom. We're not on any particular campus. It's not even regular school hours. This is what the classroom of the future will be. And what's good about it is the people attending are the ones that are passionate. They see the relevance, the enjoyment in what the science or the activity is about. And of course, tonight, it is about hands-on, but it's done in a very different way. So I just want to congratulate all the educators and of course you, the students, who find interest and relevance in this, because I find your learning will be exponentially increased simply because it's you that's chosen to attend. No one's twisting your arm. And it is an exciting session led by Miss Vanita and her team. So congratulations again to all the educators and to the students who wish to participate. Enjoy. Thanks, Vanita.
Thank you, Matthew. Very encouraging words. And yes, it's a slightly high level, but I'm sure we will go to 6, 7, 8 also with these apps and explain them motion and all. Naman, you all are going to do that in your campuses. Over to you, Neeraj ma'am. Would like to listen from you, your view, because you have taken the first session of From Fear to Fascination Smart Lab in hand.
Yeah, in fact, I just joined late, but I was listening to the conversation. And when Ravi said it's like students' initiative, I am really happy to know that. And yes, these children can actually teach us a lot. In fact, tracker software, one of my students had used. I just had to tell him, and he had to watch the tutorial. And he actually, I invited him to teach my students of 11th now. So yes, children, I'm very happy to know that you've taken the initiative, and I'm curious to see what exactly you are showing us. Would be a great learning for us as well. All the best, Vita, and keep it up. Yeah.
Thank you.
Thank you so much, Neeraj ma'am. Matthew sir, I'm going to switch off my camera. Over to you, Ravi sir, and our rock star Naman, Kavya, and Rishabh. Thank you.
So I'll just say, like in science, we study about theories, we come to know about the things, and the only way, to justify the theory, we do experiments, and after doing experiments, we try to analyze that experiment, and with the help of mathematical model, we try to understand, right, in a better way. So over to you, Kavya. All the very best.
All right. So today we're going to be looking at GeoGebra, which is a graphing software, and Tracker, which is a video analyzing tool. So I'll be talking about GeoGebra, and Rishabh and Naman are going to be talking about Tracker. So GeoGebra graphing software, basically a software where you can draw graphs. I'll just open it on my laptop and I'll screen share. Give me 1 second. Okay, so this is what GeoGebra looks like. It is basically a graphing software. You can customize anything you want. You have points, lines, perpendicular lines, shapes, orbits, ellipses, angles, and like a lot of different things that you can do. You can draw all sorts of graphs over here. Basically, they can be as complex or as simple, or essentially like anything you want. This software allows you to do everything graphically, but that's not it. You can also use GeoGebra for physics, and you can also use GeoGebra to right now what I'm going to show you is using GeoGebra for finding out angles of inclined plane. So I'm going to screen share my entire screen, and I'm going to show you how we'll do that. All right, so firstly, we're going to need a picture of an inclined plane. I'm just going to type inclined plane and select a picture that is very relevant to everyday life or probably something interesting. So about this, so this is a picture of a roller coaster. I'm just going to copy this image and then go to GeoGebra and paste this image. And you see the image that has been uploaded on GeoGebra. So all that you have to do now is find out this angle that this image forms with the base arm of the angle. I'm going to shift this to the x-axis so that we have a point of reference. All right. So in GeoGebra, we see that there are two arms, like basically there are two arms to every angle. So this is the first arm and this is the second arm, which is right above the x-axis. What we do to make sure that we measure it correctly is that we draw two lines so that we can analyze what the arms are. So this is the first line, which is the first arm of the angle, and this is the second line, which is the base arm of the angle. And we have to make sure that this line is straight for it to properly work out. All right. In GeoGebra, we can customize everything. So if you want to, let's say, change the color of a line because you can't see black contrasting, I'll just make it my favorite color. And you can change thickness, you can change opacity, you can change style, you can change almost everything. And I'm going to do that. I'm sorry. I'm just going to quickly change it again. I'm just making it something that we can all see. Yes. All right. So here we have the proper diagram of a roller coaster. And all that we have to do now is go to the tools that GeoGebra has listed down over here under the name of angles. Select the 3 points between which the angle lies. So over here it's C, D, and E. So we just select that. And right here we get the angle, which is 25.98. We can shift this. 1 second. We can shift this. My computer is not cooperating, but yeah, we can move this over here so we can see the angle more clearly, and it's approximately 26 degrees, so 25.98. And we can use so many pictures, like you can see pictures of inclined plane. We have like all sorts of images if you want to figure out their angle, and we can do all of that using GeoGebra. And that's not it. So if you just type physics using GeoGebra, like I have typed here, and you can see a variety of various simulations that you can perform on the software. One of my personal favorites is prism. One second. Yeah, right here. So this is refraction using a prism, and you can see the different angle of incidence and the angle that the prism forms and how it affects refraction. Something similar to this is what we're going to try right now after the presentation of Tracker, where we're going to look into lenses, thin converging lenses, and how they form images, both real and imaginary. But right now, we're going to move over to Tracker, which is Naman and Rishabh. Thank you.
Thank you, Kavya.
Thank you.
So I'll just share my screen. Give me a minute. I hope it's visible.
Yep.
Is it still visible, the presentation, like presenting? Yep.
Yes.
Yes, thank you. Okay, so we'll be now telling you about Tracker, something of a big event today, right? So Tracker is a free video analysis and modeling tool built on the open source physics Java framework, right? So we can use it to extract data about the motion of an object from a video. It can plot graphs from a spectroscopy and much more. Here, the limit is your imagination. It can be used to automatically track objects. It uses computer modeling to model graphs from an input, right? Like a video or maybe a picture. If you have a picture of a spectroscopy, you can insert it there and make graphs using all the info that is there in the picture. Right, so now I'd like to ask Rishabh to present his Tracker project.
Also, Naman, if you can copy paste the link in message box, so if some student wants to do side by side, they can do.
Yes, I'll just share a link to download Tracker right now.
And same with Kavya also for GeoGebra software.
Okay, thank you, Norman. So, hi everyone, I'm Rishabh, and I worked on a Tracker project on something called kinematics or 2D motion, right? In my project, I found a video of someone throwing a basketball in a hoop, simple, right? And basically, I just tracked where the ball was going and looked at all the information I could gather. So again, while I'm actually showing my project, I will be explaining how you can use Tracker. So yeah, okay, I'm going to present my screen now. I believe my screen is visible.
Yep.
Yes, it is.
Okay, so Tracker, this thing right here. I'm just going to close this because again, why not start from the beginning? So just look up Tracker because I have it downloaded, right? It opens up. So you're greeted with a blank screen, right? And this is where you can, insert your video that maybe you recorded yourself or you find online. So again, you can download, just by the way, you can download videos from YouTube. So just give me a second. Okay, I'm so sorry about that. So, right, I found this video online, so I'm just gonna, input the video by simply clicking this folder right here. And again, this is the video I found. Loading. Okay, so now that your video is loaded, well, my video is loaded, right? Now I actually know what exact frames I have to go to for my video. So that's where I want to start tracking the motion of the ball. So what I can do is, if some of you don't know what frames basically are pictures that combine to make a video. So you run those pictures really fast and those make a video, right? So I actually know the exact picture I want to start my tracking with and where I want to end my tracking with, right? So I simply right click on my video, right? And this menu opens up. I go to clip settings and it gives me the option of either choosing the start frame and end frame or the start time and the end time. And again, the frame rate and all that, don't really need to care about that. So I kind of memorized which frames I need to start and stop at. So right. So these are the frames that I wanted to start and stop at, and I can just go to the start of the video. So right now, as you can see, this right here is the basketball, and this is the object that I want to track or with using the software, right? So how do we actually start beginning tracking this ball? Before we actually, use the auto track function of this software, what we first do is we simply we calibrate the picture, right? Because we need to give the software a sense of distance, right? And dimensions in this picture, in this video, right? So what we simply do is we click on this little thing here. And this basically, I mean, I think all of you have seen this on any graphing software, or if you've even made a graph, you probably start off with something like these, right? So you simply drag it to wherever you want. Now, in this case, the ball will end right here near the hoop, right? So maybe I can keep my y-axis close to that. And well, the x-axis closer to the ball. So maybe I move it a bit up, right? So this is the thing where this is where I want to start. Or maybe I could just, do this. Why not? With the person at the, actually, you know what? No, I'm going to do this. Anyways, well, that was right. So now that we've actually put the two axes in here, we've made the grid, right? Now what we want to do is actually tell the software that, oh, this much distance actually is this much distance in real life. So for that, we just go to this thing here. We go to calibration stick, right? Because it's easier instead of actually marking 2 points. Here we know that those points are fixed using a line. And so it automatically gives you 1 meter for this. Now, of course, that's not true, right? Because again, videos can have different sizes. It all depends on how close you were or how further away you were, right? So all I have to do is drag this to the bottom and drag this part up here. Now, how do I know that? How do I know what height this blue stick is? Giving out. I just looked up the dimensions of like how high is a basketball hoop from the ground, and it usually is about 3 meters up. So I can simply click on it. So it's 1 meter here. I just write 3. So now the software knows that, okay, so this blue stick marks out 3 meters. And now all the measurements it will make, all the dimensions it will output will be like, will actually look at and refer to these 3 meters. Okay, now, so we set the scene up, and now for the actual tracking, which is the fun part, because we don't have to do anything. After we click a button, it just starts automatically. So as you can see, track, the option right here, the button, we just click on it, we click on new track. Now it gives you a bunch of options. Naman might talk about this more later on. For the purposes of this experiment, I used a point mass, right? And all I have to do now is just select my mass. So in order to select a mass to tell tracker that, oh, track this object, we simply press Control, Shift, and left click. And as you can see, the auto tracker window has opened up. So, so the software now knows that, oh, I need to track this object, which is the basketball. This is its template, right? Now, how the software actually works is, it's just going to search for this template in all frames. So it'll move frame by frame. Here we know that this is frame number 1997, right? Which is where I wanted to start. So now the software knows that, okay, in 1998, I need to search this. In 1999, I need to search this template, and so on. So pretty simple. And where does this the software look for where does this look for your template? In this dotted red box. Simple. So without further ado, I will begin the tracking. Now, all I need to do is I just need to search, click on search, right? And as you can see, it started tracking. Now you see these, I don't know, diamonds, right? You see these diamonds? Those are different points in which it tracked the position of the ball. Now, as you can see here, it already started making the graph for me, and it actually ran into an error. Wait, let me just, I think this is better. Yeah, so as you can see, it ran into an error, and it says frame 2001, a possible match was found. So the software is basically not sure if this is the object you want to track. You can basically help it. So I can check, yes, this is tracking the correct object, and press accept, and again until it starts again. So it's just keeping going, and you can look at the graph. It just keeps plotting them for you, and you can see your data is being represented here, right? So the first one is for distance along the x-axis, and the second graph is for the distance along the y-axis. So again, y and x, right? So again, it ran into an error, so I can just press accept. Okay, now there's a different sort of error. It says no match was found in the search area shown. So again, I can just skip this, why not, right? And yeah, it's fine. Okay, so you keep on going, and I think we have reached the end, frame 2049. Okay, so now we have all our, we've plotted every single point we did want to, frame by frame. I mean, we didn't, the software did for us. So this is what the final graph looks like along the distance covered when plotting the distance against the time, right? And the same thing here. And again, the same data is represented in columns over here. So now I don't need to tell you with like all sorts of things you can do with this data present, right? So maybe just finding the general acceleration, the turning points, and all that stuff. You can find all of that here, right? So you have the distance. You can also find the speed, of course. So. Right. So this is basically it. This is all I had to do for my software. I just found at what speed he was throwing the basketball, and just wanted to see how much time it took for him to actually make the shot. And I looked at the distance covered along the x-axis. Yeah. So that's about it. And again, it's a very useful tool because I plan on. So again, I have to do something. We have to do something called an IA in the second year of our diploma program, right? And this is actually a pretty useful software for that. So if I do decide to do something related to motion, I might just use this. In fact, I can use this for practically anything, as Naman will further elaborate. I actually know a friend who's using the software to do his IA. So yeah, if you want to do some experiments at your own house, you can probably just This software will give you a bunch of data that automatically that you won't have to do much work for, and then you can build your research study on the basis of this data that you've collected. So yeah, thank you everyone. That was my project.
So, may I, Rishabh, if before Naman starts, is there any doubt or any question from the students who have joined? So you can ask.
Yeah. Any questions? Anything you can understand about how the software works, at least in what I explained?
Any question by anyone? As Rishabh said, you can do many experiments. You can take a cantilever, oscillate.
Correct. So Naman will be presenting his project now. So maybe we can wait for
Neeraj ma'am
questions
wants
after
to
that.
say. Neeraj ma'am wants to say something.
Yeah, I just wanted to say, Rishabh, when you said that you could even find velocity and acceleration, how are you going to do that?
Yeah, I mean, my bad. I actually misspoke. Like you can't find the acceleration, but you can still find the velocity because again, you're given the
No,
distance.
if you go to columns,
Yeah.
there is a section columns is there. If you
Yeah.
click there you are having a AX, AY, and acceleration, velocity. You know, all
So, yeah,
all
you
other
can
things
just
you can
check all of
find
these
out.
boxes.
Yes,
Just click
yes,
and
yes.
Yeah, actually, if you click on the y-axis where it is written y, na, you'll see all the options. Just click on that.
Right here.
Yeah.
Yeah.
So that way you can locate the various graphs as well,
Yeah.
right?
Hmm.
And
That is one thing. And the columns is another thing, like Ravi sir pointed out. Yeah. Very
also,
good. This is really nice.
yeah. Also, Neeraj ma'am, last exploration, whatever we went from our school or probably from your school, everybody used this video tracker, right?
Yeah.
Because children were sitting at home, so even my children also. So it's a very good tool. And yes, number of students are less because 11th graders are having exam. They have requested to record, so I'm recording Rishabh,
Not
and it will be uploaded on YouTube. And afterwards, any doubt or anyone wants more, we will take more session. Over to you, Rishabh. Thank you.
Yeah. I
just
think
would like to add one thing here. Not only for physics, but for any mathematical model also we can
Yes.
use it. Even the students doing IA in mathematics, they can find a lot more things, a lot more data over here related to astrophysics. Apart from that, spectroscopy. It depends like what they want to do.
so. Thank you.
Trajectory in maths can be. Yeah, over to you, children.
Yeah, thank you. That was it for my presentation. Naman, would you like to carry it forward?
Yes, thank you. I'll just share my screen again. I hope it's visible again. Yep.
Yeah, it is.
Okay. So the project that I'll be presenting is that of a simple pendulum, right? So to first of all understand, like if you want to actually do some analysis on that experiment, you first need to know the concept, right? So a simple harmonic motion is a special type of periodic motion, right? Where the restoring force on the moving object is directly proportional to the magnitude of the object's displacement and act towards the object's equilibrium position, right? So in the sense, if you pull a pendulum from its equilibrium position, like if it's just standing like that, right, and if you pull it, the the angle that it makes with its equilibrium position, that is actually a displacement, or the change in angle. In this case, displacement will be more in terms of distance, right? But here it will be a change in angle, right? So changing that angle, we know that the higher the angle, the more restoring force there will be in the starting, right? So the faster it will move. So that is the thing that is explained by simple harmonic motion. So a pendulum is an example of a simple harmonic motion, but only for smaller angles, right? As you go for larger angles, the discrepancy between simple harmonic motion and the actual behavior of the pendulum is a bit higher, right? So today we will observe the damping effect in a simple pendulum, right? Using the experimental analysis that we do. So to understand damping, we must first understand some terms related to SHM. Right. So first of all, amplitude. So amplitude is defined as the maximum displacement of an object from its equilibrium or mean position. So like the angle that I was talking about earlier, moving it from its mean position, right? So that will be its amplitude. Whatever initial maximum position that you took it to, that is the maximum the object can attain then, right? So the next is the time period. So the time period is the time it takes for an object to complete one full cycle of its periodic motion. So like here you can see one cycle is shown in red. So the time it takes from this part to this end, right? That's one time period, right? So such as the time it takes a pendulum to make one full back and forth swing. And then frequency. Frequency is just the number of oscillations per second, right? So that is just the reciprocal of time period. So now damping. So the damping effect is the effect where the amplitude of a simple pendulum decreases exponentially. That is, it first decreases sharply and then goes on decreasing slowly as you proceed. And so it is due to an external force like resistance or maybe friction. Right, so now we'll move on to the tracker. I'll just share my screen again. Yes. So the project that I'll show is already done. I'll also do another one with you, right? So this is the one that I made. It is a long video. Here you can see the graph also, right? It's the maximum point from zero. It goes on decreasing, right? So that is what is a damping effect. I'll just play the video once, right? If you see, it moved to that, then it will return to a bit lesser than its original position as more and more revolutions happen. See here, the discrepancy just keeps on increasing, right? So that is what is the damping effect. Right? We could let this video go on, but it's just that it goes on decreasing like that. Here you can also see the graph. I've just put it in one dimension, right? But you can also observe it in two dimensions if you want, right? In the x and y direction, right? Because we have a coordinate in the y and the x. And it's decreasing in both because the height it attains is also less than before, right? Now it has reached to its end. And so now what we can do is maybe do one together, right? I have another video already prepared. I'll just open another tracker window. Yep. Right. So I hope my screen is visible. Yes. So generally, it is preferred that the video that you chosen is already edited. Like the starting is where you actually want to start tracking from, and the ending is where you want to stop tracking, right? Because it just makes your life easier instead of moving this end point and the starting point here and there. So the video is this SHM. Right? So open, and yes, here we go. Right, so we'll just play it once to see if the video is, yes, it is correct. Right, if we just take it here, yeah. Right, this is starting position. So like Rishabh also told, first we need a coordinate system, right? So just to give a sense of X and Y direction to the software, right? That okay, this is the zero position and this is like maybe one or whatever, right? I just kept it here so that we keep it so that it's mean position is at zero, right? It just makes our calculation and a graph a lot easier to read instead of having to see a mean position that is actually a number greater than or less than zero, right? So there's a coordinate. Then we add a calibration stick, as Rishabh did. Like maybe let's say this is about 1.2 meters, right? Instead of keeping it one, let's keep it at 1.2 meters. Right? And what we need to do is create a new object. So we go to just track new object in a point mass. You can use as you like a center of mass if you actually are uh, like tracking the center of mass of an object. But since what we're tracking here is the nozzle of the spray paint, right? So a point mass is easier to use, right? We also got the graph of this. So like earlier, we just hit Control Shift and then click on the nozzle because that is our template. Right? That is what the template we want to use. Right? So here is the template chosen, and now we simply just click try search. Now here you see it hasn't found a match. It is sometimes fine to skip it, but it is generally preferable that you don't skip it. So what you can do is you can manually set like, okay, here is the point. So you just click shift. You don't need to click control this time, only shift and then click whatever you were searching for. Again, it is doing that. It is again click it again. It might happen a few times sometimes, right? The software isn't able to track it sometimes, but it generally starts happening like here. You see the math score was 1.2. So it generally gives this error when the math score is less than 4. Right? So less than 4, it is a bit skeptical like, okay, is it the object that you're looking for or is it not? And generally it is. It's just that the frames are a bit blurry. So the software is not that sure that it is what is it should be looking for. You just click accept and now it is just continue searching. So this is a fairly long video again, but this will also give you an idea of how a simple harmonic motion, because this is also an example of an SHM, and actually a better example of SHM than a pendulum, and because it stays a lot more constant, right? It stays a bit more, the word like maybe not so discriminant, right, from the actually SHM working. It will just continue. You can see that guy is pulling on a thread there to move this paper which is rolled along the sticks. See, so that is how the graph of it looks like as well. If we go here, right? If I just move it here, you see the graph, and this is what we call a sine or a cosine curve, right? So sine and cosine, they're fairly similar, right? So this is what we call a sine or a cosine curve. Like Kavya also showed a graph of a sine, y is equal to sine x. So this is what, so the sine curve or a cosine curve actually explains SHM. So in science, right, if you get a sine or a cosine graph like that, just physicists get mad, like, yes, they found something useful, because these are some of the most useful functions to work with. Like, see here, the tracking score is fairly high, right? But whenever it goes below 4, like 3.9, it stops. Like, okay, is it what you're looking for? You just click accept. It is mostly what we're looking for. And we don't need a lot of precision here, right? Because the video is not of that high resolution anyways. But if you actually need precision, you can maybe try and check by clicking shift and control, and so that it clears up everything, and then you can see, like, okay, is this what I'm looking for? If what you're looking for is inside the circle, that's good enough, right?
Naman, can you remove this auto tracker mass
Uh,
box?
yeah, I can move
This-
it here a bit,
yeah.
right? Because that is needed to keep searching, you know. Here also you can see the damping effect, right? As you go on, it just keeps decreasing. Right? You don't need to think of the x a lot, because here what we're measuring is only in the y-axis. The x-axis is only because of the wobble of how the person actually pulled on the spring, you know. This is what we called as a Hooke's law. You see here the equilibrium position is close to zero, not exactly zero. I didn't place it that well, right? But you can also change the coordinate if you want. In mid, like if I want it here, okay.
You can also click on y-axis and see what other information it can give.
Yes, you can
Frequency
see all the
interesting. Yeah.
like the y, the
Angular
position.
acceleration, angle. You can solve numerical also based on this, collecting these terms.
Yes, so that is the thing of tracker. It gives you the mathematical data that you need to actually start calculating more quantities that you might require, like the acceleration, or maybe you are calculating the uh, spring constant for some specific spring here, like that. Right. So now it's complete. You can close this window and then we can now finally see our video from the start, right? Just so that we can get sense of accomplishment. See, right? And there are graph also. We can make the graph a bit bigger so that it's visible. Yes, right. We can keep it in one dimension because we only need to look at the y coordinates in this particular experiment. So that skip thing, you can skip it in between if it's not that, if you don't need that much precision, because there's an option to autofill the missing coordinates as well in tracker. You find it over here if you skip any, but that's obviously not as accurate if you actually measure it from experimental data. It might be a bit different from what the actual value you're getting as compared to what the computer predicted. So here also you can see the damping effect, right? The amplitude of our spring is decreasing gradually, right? Because this is an experiment, it's not completely exponential, right? But mostly exponential if you just draw a best fit line of with an exponential line, right? So you can also see here the sine curve or the cosine curve, whatever you like.
Children can also explore, the same experiment. Right now it is oscillating in air. And once I tried with some oil in that a jar and I allowed that thing to oscillate. So how damping is different from air to oil, etc. Those type of exploration can also be done with these children. So, this is just a software, but there are many things you can make changes, you can vary, whatever you want to do, you can do different oils, type of oils, and where damping is more, less, why, etc.
Like here you see I did it by mistake, but you can also rotate the axis if you are doing maybe some inclined plane experiment where this is a lot more easier to think about than maybe putting a coordinate system like this, right? Because these coordinate systems are meant for our reference. And so
Yes.
this gives us a reference point like, okay, this is where the motion is like maybe in its mean position or we are because physics is mostly about what reference point you choose. Like if you're checking velocity or displacement is totally based on reference points. Like okay, what is your starting point and what is your ending point, right? So here you can easily change your reference points, right? This distance is based on your actual experimental setup. So yeah, that is what we have done another one together, right? So if we go back to the presentation now. Right, so some more projects that we can do is this measurement of the sidereal David tracker, right? Some astronomical quantity, right? I'm not so sure. We'll study this in second year, right? That's these are some experiments that people did with tracker, right? This is the tracker window that they did. Collision theory, right? Rotational mechanics, free fall, deflation of a bubble, Snell's law, analyzing the solar spectrum, like this graph is the luminosity versus the wavelength graph, right? The emission spectrum of sodium of lamp, right? The continuous spectrum, and so much more. Tracker is, you can do anything with Tracker as long as you can think of getting a way to getting Tracker to because Striker is a very versatile software, right? So if you have the imagination, you can do a lot of things with this. The things that we're showing us, these are things that are done by other people in universities or maybe um, individuals and all, right? So if you want some reference, there is also a very useful thing in Tracker where you can go to File, and this is called the library browser. You can access public experiments that people have done with their own, like go to collections, and then you can go to this Compadre Digital Library and OSP. And so this is what we mostly think about, right? Like experiments in astronomy, classical mechanics, education practices, fluid mechanics, mathematical tools, modern physics, optics, oscillations and waves. These are just you can do a lot of things with Tracker. That is the thing.
I was thinking, Naman, sometime you should do when the exams are over and more children are there on mathematical tools also. Because yeah,
So
we as a physics teachers are using trackers a lot. Many time I tell children to record some video when they are going back to school, from school to home, and just analyze with this. So keep thinking and keep doing. You have smartphone, but when maths come now, there how to apply this. Even I have to explore. So probably that also will be very interesting. Over to you, Naman. Thank you.
Yeah, so that is what we have for tracker today, right? Like all these experiments.
So
Yeah,
would like to listen from expert, Neeraj Taneja ma'am.
and
No,
there's another thing
I'm no
done by
expert.
Kavya
You
also.
are.
No, in fact, Naman, you took up a very, very interesting topic, that is of damping, because now normally we talk about in theory about these sine curves, but tracker shows a proper sine curve, and that's amazing, you know. And you explained very nicely. I'm just hoping that you should be able to make your own videos and then analyze them,
Yes.
because
Yes,
these
the
were
point
the
of
videos
tracker is
that
to
you
do
took,
it
yeah.
yourself. Yeah.
Yeah.
And there also you'll develop a lot of skills, because creating a video which is not shaky and having your own calibration stick also, you, because you know, as you mentioned, there is a calibration tool also required. So there in that video you have to have a calibration stick. You have to see that the video is perfectly straight, it's not inclined. And so there's a lot of skill which you will require in that case. I just hope that you will explore that aspect as well, because when you talk of your own experiments, you have to create your own videos. And using, as you mentioned rightly, this is very important, using the correct reference point, orientation of the axis. That's also, that plays a lot of role in deciding the precision of your data. And when you mentioned spectrum analysis, yes, that's very interesting. I tried exploring it once, but couldn't get into the depth of it. And now, when you mentioned, you reminded me that I have to explore, because it's slightly different. The calibration there required is very different than what you do in mechanics. But that's a very, very interesting tool. Very nice. It was nice listening to both of you, Naman, Rishabh, and in fact, Kavya also took up a very, very interesting topic, GeoGebra. Very nice
I
job.
have a little bit of my topic left out.
Okay, great.
It's,
Please
Kavya
carry
will
on.
take it further right
Yeah.
now, GeoGebra, which is interesting. Also, Neeraj ma'am, when you said last time when we were doing helicopter chopper experiment and we were, taking video, we failed twice, thrice. And this was Nandini whose project says, ma'am, we are not getting that point. Okay, then one mobile here, one mobile here. Because we wanted to calculate angular velocity and along with that. So Naman, rightly said by Neeraj ma'am, you will take your own video and then you analyze. You will really learn more. Thank you. Yes, over to you, Kavya.
Okay, so final thing for the day. Okay, I'm so sorry for that. Final thing for the day is GeoGebra, where we simulate thin converging lens. And so I'm going to take you through how exactly that works. And if you have GeoGebra installed, and uh, the link is in the chat, you can follow along if you'd like. So GeoGebra has a lot of tools that allow you to make a thin converging lens. And for reference, I'll just show you the diagrams of a thin converging lens. One second. This. So we're going to do all of this using GeoGebra. I'm just going to unzoom and put it to a side. Yes. All right. So what we need first in order to make a lens is in fact a lens. So for that, we're going to go here. We're going to take an ellipse. And for an ellipse, we take 2 points. 4 seems good. And we'll take negative for here and height. Yes. So now we have formed a lens in order to do our simulation. We can also get fancy and we can go here to settings and we can choose whatever color we like and give it a little opacity for the aesthetic effect of it. And now, what we've seen when we drew such diagrams is that we need to have an object. And in order for us, I'm sorry, in order for us to have such an object, we'll just make a point, which is the highest point of an object. And I think this point seems fair. So this is our object right over here. We're going to mark the center and we're going to mark the focal point. And I think we should go with 3, and focal point is both sides. Give focal point on both these sides. I'm going to rename this to focus and go to settings And for the aesthetic of it, change this one and this one. And rename this to focus. Yes. And rename this to object. Okay, I can't spell. I am so sorry. Object. Yeah. So this is what we have right now. And in order for us to move this object here and there, we need a reference point, like Naman emphasized upon the importance of reference point. And this object will move with reference to the x-axis and the y-axis. So what we do is we draw a line that connects this object to the x-axis, to the y-axis, and this object to the x-axis. GeoGebra is very convenient. It simply has a tool called perpendicular line. We select the object, we select the y-axis, we get a perpendicular, we select the object, we select the sorry. We select the object, we select the x-axis, we get a perpendicular, that's it. Very simple. And now we can see the motion of the object in reference to the to x-axis and y-axis. Now what we've also observed is that whenever we write draw a diagram, we see that the ray from the object passes through the central point. So we just go over here, draw a line from the object to the central point. Also, all rays emitted from the object converge at the focus. So for that, we go over here to intersect. We intersect this line and the x-axis. We intersect this line and the y-axis, and since all rays converge at the focus, we make a line that converges this ray to the focus. That's it. And since objects usually, as you can see over here, objects usually they're depicted using an arrow right over here, as you can see. So let's just draw an arrow in our diagram for our own convenience and for it to look more like what we've been doing for so long. So we just go to lines, go to vector, select the object, and that's it. We have a line, and we can't see the line because it's camouflaging. So we just go to settings, we go to color, we change the color. I'll just take red. And we go to style. Sorry, I selected the point one. We take the vector, we go to settings, we go to color, take red, style, make it thick. That's it. So we have the object ready, and now you can see that the rays that are emitted from the object, you can see them converge over here. If you think that these lines are unnecessary, we can just hide them. So here you can see how the rays converge as the object moves. But now, in order for us to show the object as an image, whether it be real or imaginary, we need to have a reference on the other side as well. So what do we do for that? Well, similar to what we did right now, we're going to go over here, we're going to go on intersection point, we're going to select the intersection point of these two rays, and we're going to drop a perpendicular again between the intersection point and the x-axis. Then we're going to go to intersection. And see the point of intersection between, all right, we already have it. There's a question. Okay, sorry. So we got a point of intersection right over here. And if we move, we can see the point of intersection move along with it. And since we need an arrow for reference, I'm just quickly going to insert an arrow right over here. And for the aesthetic of it, I'll just make it any color, let's say this one. And style, make it, add thickness to it. All right. So this is it. This is essentially all that we have to do for us to make a simple lens diagram on GeoGebra. And you can see now we have the different situations listed out over here. Let's try all of it. I'm going to zoom in, and the first one is parallel lines, which basically shows that an object at the focus, which is F, does not form an image because the rays are parallel, so it essentially forms an image
At infinity.
at infinity. Yes. So as you can see, the rays don't converge, so there is no image. Between f, since f is 3 and 2f would be 6, so between f and 2f, if our object is there, then the image will be formed beyond 2f. And beyond 2f, if our object is placed, then the image will be formed between f and 2f. And if the object is placed between f and the center, then there'll be an imaginary image that will be formed in the same plane. And that is how you can simulate thin converging lens. If you find these lines annoying, we can simply stop showing them. And for these, we can also, GeoGebra also allows us to change the style of a line. So we can make it dotted for our convenience right over here. And that's it. That is how you do thin converging lens, and you simulate that using GeoGebra.
Kavya, when you were in grade 10, you learned all this by just sketching, right? If you would have known this and would have played, it would have been, mind blowing and a very aha moment. So I'm thinking something keeping you three in mind, and probably will send you guys in IGCSE 9th and 10th grades and just half an hour and teach all these students along with, and let them play and let them explore. Over to you, Krishnan, because these are the few.
I will
Yeah.
just add one line.
Yes,
I
sir.
really proud all of you. Like you really presented very well, and kudos. That's it.
Your
Krishnan sir, over
students,
to
Thank
you.
you.
your students, Ravi sir. So over to you,
Thank you,
Krishnan
miss.
sir.
Yeah, thank you. Mr. Ravi, can you hear me? Can you hear me?
Yes, sir,
Yes,
we can.
yes.
Thank you. Thank you. First of all, very good evening to everyone.
Good
Ms.
evening.
Tanuja, Mr. Ravi, Ms. Vinita, and all the students. Ms. Vinita, before I start, is the students of Gurgaon School is also here, DP students?
Few students.
Few
We have,
students
we
are
have
here.
kept recording for CBSE kids who are having exam.
Okay. So I'll take maximum 3 or 4 minutes. Okay, just my observation. Obviously, whenever these kind of sessions are happening, I always want to be there. So that's why, though I got 5 minutes late, but I always enjoy these sessions. That is one. Second, tell me, Naman, Kavya, and Rishabh. Quick question: did anyone taught you these two things about this tracker as well as the GeoGebra, the features and everything? Be honest, yes or no?
No, sir. So Ravi sir just introduced Tracker to us, and then we'll use like we just figured it out on our
Very
own.
good. This is the answer which I was expecting from everyone. Now this is the message which I am giving it to all other students. Okay. See, remember when I say with respect to DP curriculum students, now IB always gives this kind of opportunity that this is a platform which is available. There is no limit to the learning part. So this is a platform available to everyone. So explore. These three students only they got introduction from Mr. Ravi. After that, they figured it out. They spent a lot of time. They explored themselves. That's why you can really see the quality today. Though they have been preparing,
They were.
that's good. Now understand, students. This is what the expectation is according to IB curriculum, right? They say only teachers can help you up to some extent. Later on, it depends on you that how much time you spend on this to explore certain things which will be beneficial for your own subjects. That is one. It's just like a mobile. You get a new mobile from the market. Does that mean anyone teach you how to go through that features? No. You spend a lot of time on that and you explore yourself, right? Well, why not in the software? Question is very simple, because that is your area of interest, mobile and other things. You need to create interest for this platform also. That is one thing. Second, I will go with the statement what Mr. Ravi has said. Not only in physics, this has got huge application in other subject, especially in mathematics. Right? Now let me start with Rishabh and in fact Naman, Kavya, everyone. Now to update you, GeoGebra and Tracker, this is the most deadliest combination. Yes, now I'm talking with respect to my subject, which is mathematics. Yes, now if you are reached to this stage that the way that you're exploring, believe it, believe it, you will come out with flying colors in mathematics IA when we are planning to start in the month of January next year, because you already know the basics and your ideas are clear, and you know that what you can explore, what will be your theme, what will be your topic, and how you can use this software extensively. Believe it, you are already prepared for that. Other students, if there are there from Gurgaon branch, I'm telling you students, this is the right time, please explore. And we always believe in kind of cross campus collaboration. these three students will be more than happy to explain you. Only thing what is required for other students is you need to take out your time and create interest to learn all these things. In the long run, it is going to help you. And believe it, these three students, that the way that they worked, it shows the preparation, it shows the quality. It takes time. The way that they are presenting very formally, I think that is commendable. That is really commendable, which I really appreciate. Okay, that is one thing. I'm sure there is, and other students, especially students, if you know this software, believe it, one is your physics, definitely another one is your mathematics. Your coming IA next year, whatever is going to happen, these two subjects, rest assured that you will be getting one of the best marks in that. Okay, so that much I can assure. In mathematics, I'm sure Mr. Ravi and Ms. Vinita will also agree with that. So that's the beauty about this curriculum, and that is what the
100%.
software is there, right? So students, please use this platform, use this opportunity extensively. Don't miss it, because as I keep saying this again, I keep saying this to my students. I'm telling this to everyone now. IAS is the only one thing which we can control, which is in our hands.
I have seen students in physics and in mathematics. They have some kind of fear. Like if you tell them, students, if you can do analysis using tracker, sir, it's very difficult. We can't do it. So actually, at this early stage, they are in DP1. They have they are just doing mechanics right now, and they have not been to waves and electricity. A lot of it is pending. And at this point of time, if they have actually faced that fear of a GeoGebra and tracker, definitely I'm very much optimistic about their learning ahead, not only in school but in your university level as well, in your life as well.
That's why the name is From Fear to Fascination, this particular careers platform we have created. I can see Matthew also still there, because it's already must be 11 or something in Australia. He generally stays for 5 minutes or 10 minutes. Matthew, are you there? Must have forgotten, because generally he introduces the this thing, and then generally he goes because it's late night. Thank you.
Yeah, and Vinita, just to conclude, so students, remember one more idea. If at all you are performing this experiment, okay, for it will be helpful for your internal assessment as well as for your extent essay, right? That is one. Secondly, if you are doing something for your physics, those readings you can use it as it is for your mathematics IA also. That is called interdisciplinary, which IB allows.
Projectile motion and all.
Yeah, so these are the advantages in the long run if you know that. So I think great job all three of you, Naman, Kavya, as well as Rishabh. So that's really wonderful to attend this session. So looking forward to have many more in future, right? So
And
great.
thanks a lot, Krishnan. Yes, sir, you are so your encouragement, and when you said GeoGebra more in maths, and I wrote, and Sunil sir replied. So that is also required, because we are creating platform, but especially Matthew, the way you all are encouraging, that's also important. So thanks a lot for always being with us for
Welcome.
all these sessions. And thanks a lot, Naman, Kavya, and Ravi sir. Please wait for 1 minute before.
Yeah, sure. Would like to hear something from Tripathi sir, if I'm audible,
Tripathi
sir.
sir is there. Tripathi sir has left, I believe. He just left. No, he's there. Tripathi
He's
sir,
there.
you can unmute. So I will stop recording now, because.
Yes, ma'am. Can you hear?